like this equation, except every time you try to use it, I mark it wrong except in one case. Because the equilibrium expression says and I said all weak acids always go hydrogen ion, anion over acid. And they said this is hydrogen ion squared. Darn. The reason for that is this is the most important one because it's much bigger K than this one. The only time you can use this, there are three unknowns here. This is the constant, of course, so that's not an unknown unless I don't give you any constants in the problem. I don't give you your book. But this is a constant. If we know two of the three, we have to be able to calculate the other one from this equation. So you have to know two of the three, you can calculate the third one. Now this differs a little bit for what your book does when it gets to this problem, because he uses what he calls the KSPA, where he combines that, and it basically is the Ka1 KSP for the problem. Don't worry about that when we get there. And that only works in acidic solution. This will work in any solution at any pH, but it has to be true that you know two of the three variables. And I pointed out when you have a saturated solution of H2S, it's about 0.1. It depends on the temperature, things like that, but it's somewhere near 0.1. And if we know the pH of the system, we can calculate what the sulfide ion is. And you can make buffer solutions. That's what we do in procedure 5 when we add the acetic acid in the HCl. We do that in procedure 15 where we add the ammonium chloride and the ammonia. We're making buffer solutions. Okay. So we will use that equation, which will differ a little bit from what the book does when we get to that problem. And the next topic is selective precipitation. Finally got there. This is what we're doing when we're using sulfide ion, and we're working with H2S, or I'm sorry, we're working with group 2 and group 3. By adjusting the pH, we can precipitate either the group 2 members in acidic solution. That's because it has a high sulfide ion concentration. Actually, it has a high sulfide ion eventually, based on this calculation, whereas if we're working in a basic solution, it had, let's go back. In an acidic solution, this is going to be small. So the KSPs for the sulfides in group 2 are large, really small numbers, so you don't need much of this to make precipitation. The KSPs for the sulfides of group 3 are larger numbers, so you need a higher sulfide ion concentration. And what happens, by the way, in this detailed equation, as you use sulfide ion up to make this precipitate, this equilibrium shifts this way to replace the sulfide to maintain that equilibrium. And as this one shifts this way, you're using up this one has to shift this way. So what you're doing, you're actually precipitating every time a sulfide ion hits a copper ion, but there aren't many of them, but the equilibrium keeps shifting to produce more and more to replace the ones that are being used up to make the precipitate. So the distinction when we're doing net ionic equations is that we're working with principal species, not the actual things that are colliding and reacting. Then, I'm going to write selective precipitation. That adjusting the pH is one way of selecting which group precipitates, and we'll do that calculation, and that's where we'll use this relationship, but we're not quite ready for that yet. So we'll start off with a simple problem. I have a mixture of and I have 0.1. In other words, I have both sodium chloride and sodium bromide. The concentrations of each of those ions are 0.1 molar. I start adding silver ion. They both make insoluble halide precipitates. So if I start adding silver ion, one of them's going to precipitate first, and then the second one starts precipitating as I slowly increase the silver ion concentration. Which one precipitates first? Well, you need some information, right? What do you need? Turn the page here. And here's silver bromide, KSP, 5 times 10 to the minus 13. Notice when I do it in my quiz, I usually give you a couple more decimal places, just so you have to give me more decimal places in your answer. And there's silver chloride. This is a much smaller KSP. That means, just looking at this one, this should form first. Now the reaction that happens, this is the reaction. This is stoichiometry. I'm not doing KSPs yet. So as I add silver ion, I'm using up bromide ion, and this concentration goes down. And of course, I'm making this precipitate. Eventually, since there's an equilibrium, now I'm going to write the equilibrium thing. As this goes down, what has to happen to this number? It has to go up because it's equal to a constant. One goes down, the other increases. So I'm slowly adding silver ion. The bromide is forming a precipitate, and the bromide ion concentration in the solution is decreasing, and meanwhile the silver ion is slowly increasing. Eventually the silver ion gets large enough, we start doing this reaction. Silver starts reacting with chloride ion to make AgCl. And then the equilibrium that we have to worry about. This one. Okay. So we just look at the KSPs for this and decide which one precipitates first. Because the one with the smaller KSP precipitates first. I'll come to you in just a second. As long as they're 1 to 1, 1 to 1. Okay, your question.
Should be, yeah, chloride.
Oh, okay. Yes. Yes, because that's the KSP for silver chloride. Okay. But suppose I had something like I had this case and I changed the original concentrations, it'd be the same sort of problem where I have a larger and smaller one. I have to decide which one precipitated first. Okay. But if I had this one here, this is still 1.8 times 10 to the minus 10. So chromate is, there it is, 1.1 times 10 to the minus 12. But because there's 2 silver ions, 1 chromate in here, you can't just look at the KSP anymore, because silver chromate does not precipitate first. Silver chloride precipitates first. We used to do, and by the way, this is a classic experiment, one of the things people used to worry about in titrations was the chloride content in blood. And so what you did was a precipitation reaction with silver ion. You titrated the chloride ion content in blood by precipitating the chloride with silver ion. And guess what the indicator was? Potassium chromate. And as you got to the end point, the silver chloride was white. This is a reddish brown color. The color of your precipitate changed from white to reddish brown, and that would tell you what the end point was. And we used to do that experiment, Chem 2, back in the days when silver was cheap, because it was directly related to something people did. Nowadays they use fancy pH type meters. I keep quitting early here because that clock's wrong by 5 minutes. I kept getting over to my office and saying, how come I'm here so early? Darn, I hate that. So I'm going to keep talking for 5 minutes. Okay, so coming back to, that was a classic experiment. We used to do it in Chem 2, and we even talked about the theory. And we don't do that anymore because we realize even after we talk about it in Chem 1B, people are still having trouble with the theory. Darn. Okay? So what you have to do to decide which one precipitates first, because there are multiple parts to this question. You have to calculate the concentration of the precipitating ion to cause the other substance to precipitate. Okay? Cause the precipitate to form. So to make silver chloride, for instance, the concentration of the silver ion is going to be, all I did was a little algebra here, right? Because here's my reaction, so it's KSP over chloride ion. It's 1.8 over 0.1, which is the original chloride, which gives me what? Right? Okay. Then I do the other calculation, and here's where people get into trouble because they don't, they're still thinking about 1 to 1 to 1, and it's not 1 to 1 to 1, so you better write it down. You still know the chromate, but when you go to solve this for the silver ion, what you're doing is solving this equation. And you can see, because you have to take a square root, you're going to get a much larger concentration of silver ion needed to precipitate the silver chloride, the silver chromate. Okay. So now we have because this was squared,